Okay, good morning everyone. In today's lecture, we will continue our discussion on neural language model. So in the last class, we started discussing vanilla RNN. We discussed the architecture of RNN and then the training of RNN using backpropagation through time, BPTT, right? And we have also seen that due to the recurrent multiplications of gradients, right? What happens is that if the size of the gradient is small, it would lead to vanishing gradient problem. If the size is large, it would lead to exploding gradient problem. So although theoretically RNN can capture long context, but in practice it starts forgetting those contexts which are far from the current context, current word. So exploding gradient can be addressed using methods like gradient clipping, right? Whereas vanishing gradient can be addressed in various ways. So in today's class we will discuss different gating mechanisms. We will discuss LSTM and GRU, right? But in the next lecture maybe we will discuss more advanced topics like attention, right? So attention, LSTM, GRU, these are different ways, but apart from these techniques there are also other ways. For example, you can add skip connection, residual connection, etc., etc., right? We will discuss all these concepts in today's lecture. But today's breaking news is as follows. So PyTorch recently released a torch chart, which is a very friendly library which you can basically deploy in your laptop, desktop, edge devices, mobile devices, and so on. PyTorch, this torch chart has already access to multiple LLMs, specifically Llama 3 billion instruct. It has been deployed on Samsung Galaxy S23 and iPhone, right? Using some sort of quantizer. As you see, 4-bit quantization was used here, and this is, I guess, this is a very interesting tool, right? For example, we have been talking about small language models, right, in this class. So you can use this torch chart and you can deploy this in your mobile, iPad, right, for quick access. And the good part about this is that this is very fast. Per second it can generate 8 tokens. That this is quite significant. Okay, so let's get started. So so we'll first look at some of the usage of RNNs in NLP, in language technology. So since RNN is a sequence labeling method, right, given any sequence, it should be able to solve downstream tasks, right? Let's say the downstream task is a task like partial speech tagging, POS tagging, right? So you are given this sequence, so this is the sequence, and you are asked to essentially determine the POS tag for every token in the sequence, right? So what you do, you run an RNN, vanilla RNN, right? So let's say there are 46 tags, 46 POS tags, right? So from every hidden state you pass it through a linear layer U, last day we discussed, followed by a nonlinearity, softmax, etc., and softmax will essentially map this to a 46 dimensional vector, right? And you choose the one which has the highest probability, and so on and so forth. We choose the one which has the highest probability, not we choose the one, we sample it from the distribution, right? Remember this, because this is not a generation task, this is a classification task. And you do this for all the words. Now here you can ask that in order to predict, let's say, the POS tag for the word cat at this hidden state, okay, I have access to only the previous hidden states, right? But sometimes when we do POS tagging, or let's say named entity recognition, we may also need to access to the future hidden states. And remember, the entire sequence is given to you. It is not a generation task. The entire sequence is given to you, and the task is to predict the POS tag for every word, right? So why only to consider the previous hidden states? We can also consider the future hidden states, right? So we will discuss in today's class that here we will use bidirectional RNN. Bidirectional RNN, there is one RNN from left to right, there is another RNN from right to left, right? So at every timestamp, you will have two hidden states, one from left to right and other from right to left, right? You have two hidden states, and then you can either concatenate or you do some operations and basically create a single hidden state, and from the single hidden state then you pass it through linear layer and non-linearity, right? This is called bidirectional RNN. Okay, you can use RNN for simple sentence classification task, for example sentiment analysis, for example, right? Or let's say spam email classification, right? So what you do here, again there are different ways to do it. One way would be you look at this sentence, there are hidden states here, one RNN, right? Then you basically merge all the hidden states together some ways and you create a single vector. This can be possible. Another possibility is that you look at you take only the last hidden state, because the assumption is that the last hidden state has information to all the previous hidden states. So you take the last hidden state and you pass it through linear layer, non-linearity, and so on, so forth, right? So the problems with RNN I mentioned last day: vanishing gradient problem, exploding gradient problem, and it happens due to this recurrent computation of gradients, right? Let's say this is the last loss of the final loss, which is j theta, right, at the fourth step, right? I discussed this thing in the last class. Okay, and if you want to take the gradient of this with respect to h1, right, you'll have to take the gradient of this h4 with respect to h3, h3 with respect to h2, h2 with respect to h1, and so on and so forth, right? And if so these gradients, right, these are essentially matrix, because you are taking the derivative of a vector with respect to another vector. Okay, now if the size of this matrix is small, right, then it will lead to gradient vanishing gradient problem. If size is large, it will lead to exploding gradient problem. Okay, so and how to address this problem we discussed last day. Now how to address this we'll discuss today, but let's look at the problem here, why this is a problem, right? Let's look at this sentence, right? So when she tried to print her tickets, she found that the printer was out of toner. She went to the stationery store to buy more toner. It was very overpriced. After installing the toner into the printer, she finally printed her dash, right? So this will be tickets. Now look at the distance between this and this tickets. The word tickets in this is, I think, at the 7th position of the sentence, and this is very, very far. So vanishing gradient, due to vanishing gradient problem, RNN won't be able to predict the next word as tickets. Okay, so what are the ways we will fix it? Using a gating mechanism, right? We will see that in a gating mechanism we will explicitly use another state called the memory state, right? So along with the hidden state, we also have a memory state called the cell state. We'll discuss. So using LSTM GRU, we'll try to address the problem of vanishing gradient, but there are other mechanisms also like attention, residual connection. We'll discuss later. Okay, so let's focus on LSTM and GRU. So what is the idea here? So the idea here is that in vanilla RNN, so these are hidden states: h1, h2, h3, x1, x2, x3 are the inputs, right? So at every state, at every time, you have a hidden state, right? In LSTM, we will also maintain another state. A state is a vector, right? We will maintain another state called the cell state, denoted by CT. The cell state will act as a memory. Okay, so the cell state is responsible for storing information which you do not want the model to forget. Okay, so hidden state and cell state, these are the two states which will be available at every timestamp. Okay, and we will control the content which is going to be written to this memory cell state using a gating mechanism. So we have a cell state, we have hidden state. The cell state will act as a memory and the hidden state will act as an output. Okay, now this is the overview. I'll discuss in details. We'll try to understand the overview of this. So memory, cell state and hidden state. Cell state will act as a memory and hidden state will act as an output, right? We will generate some content which we want to store within the memory, right? But how much of this content will be stored into the memory, this will be controlled through a gating mechanism, right? And what are these gates? These gates are similar to AND OR gates that we have that we already know, but not as simple as that. But the idea is more or less same. So gate itself is a vector. It is also a vector, right? So a vector has multiple cells. If one cell is, the value of one cell is 1, it means it will allow the information to pass, the corresponding information to pass to the memory. If it is 0, it will not allow. If the number is in between 1 or 0 to 1, let's say 0.5 or 0.3, proportionately the information will be passed, right? So in LSTM, we will see there are 3 kinds of gates that are being maintained, right? Now these gates are responsible for deciding which part of the content I would like to store into the memory, how much I would like to read from the memory and store into hidden state, right? So these operations are very similar to the operations that we have in computer, read and write operation, right? I write something, right? So here I write the content to the memory, I read content from the memory and store it to the hidden state. Okay, and how much will be stored, how much will be forgotten, how much will be written, all these decisions will be taken by the gates. Clear? Now these gates, the values of these gates are controlled dynamically. Okay, in fact these are the parameters. Okay, values of these gates will be controlled dynamically. Gates are vectors like this. Okay, values, generally the value of every cell of the gate ranges between 0 to 1, right? If it is 0, then it will not allow the content to move forward. If it is 1, it will allow the complete content to move forward. And if let's say this is 0.3, so it will only allow 30% of the content to move forward. Okay. Let's look at it. This is very important. I'll go slow so that you understand it. Okay, so now as I mentioned, at every time t, okay, there is a cell state ct, there is a hidden state ht, right, ht. Okay, this is at every time. Similarly, at t minus 1, we have a cell state ct minus 1. Let me write in this way, t minus 1, right, and a hidden state h t minus 1. Okay, so there are 3 gates that we will create, right? One is called the forget gate, ft, forget gate, right? The second one is called the input gate, IT, and the third one is called the output gate, OT. Let me explain the functions of these 3 gates, right? So I will discuss these equations later. First, try to understand the intuition behind this. So the forget gate controls what to keep versus what to forget, right? So now remember, at t minus 1 is timestamp, you have some information stored in ct minus 1. Either you want to move the entire information from t minus 1 to t, or you want to move a part of this to t, right? So how much you want to forget and how much you want to move will be decided by f. Okay, so you will see that if will be attached with ct minus 1 if we'll decide how much content, right, you want to basically move from ct minus 1 to t, right. So what is IT? IT is the input gate. What is the role of the input gate? The role of the input gate is to decide, right. So remember, at every timestamp you generate some content. T minus 1 is timestamp, you generate some content. And how do you generate the content? The content will be generated based on the current input and the previous information, right. At this timestamp you generate some content, and then we'll have to see that how much of this content that you generate at timestamp t will be written to the cell. Now remember, a cell will have information from the current content and from the previous content. Where was the previous content stored? The previous content was stored in the cell state of previous timestamp, right. So how much the previous cell states content will move to the current cell state, who will decide that? Forget gate. And how much the current content will be stored to the cell, who will decide that? Input gate. Clear? And then we have, so far there is no role of hidden state. We are just deciding how much amount of information you want to store into the cell state. Now we have already decided, let's say we have decided cell state has been updated. Now from cell state, how much information you want to read and store it to the hidden state will be decided by the output gate, right. So output gate controls what parts of the cell state are output to the hidden state. Let's look at how these gates are formed. So you see here, all these gates F, I, O, they are functions of the previous hidden state, right, and the current input, right. And what are the differences? The differences are the weights. For the forget gate, you have two sets of weight matrices, WF and HF. For the input gate, WI, HI. For output gate, WF, UF, WI, UI, WO, UO, right. And these matrices we need to learn. And along with this, we have bias. Just ignoring the bias for the time being, right. So all these gates, values of these gates are decided by whom? It will be decided by xt, right. It will be decided by xt, okay, and ht minus 1, okay. It will be decided by ht minus 1, correct. Clear? Okay. Now what is the next task? The next task is to generate the content at this time, right. So the content that we will generate, this is not the cell content, this is the content that I want to write to the cell. This is called cell content. This is the content that I want to write to the cell, okay. So the cell content C tilde at time t will be generated based on the previous hidden state, same, based on the previous hidden state and the current input. But look at the parameters, parameters are different, WC and UC. So a cell content C tilde at time t will be generated based on ht minus 1 and xt, okay. Now this is the content that I would like to write to the cell state, okay, but my forget gate and my input gate will not allow to write this totally to the cell state, right. So here this forget gate comes to the picture, ft, and ft will say that, look at here, ft and ct minus 1, right, they are connected through this element wise multiplication, right. So ft will decide how much of the previous current state, previous cell state will be moved forward, right. So ft, through ft, this will come here, and through it, the cell content that you have just generated will basically come to the memory. So through IT, this is IT, through IT, it will come here, right? So the cell state is essentially a function of the previous cell state and the current cell content, and it will be controlled by forget get and input get. Clear? So based on this, we will update the values of the cell content of the cell state, right? Now, how much I would like to basically write or read from the cell state, it will be decided by OT. So you see here, right? How much will be how much we would like to read from the cell state and write to the hidden state will be decided by OT. So OT again element wise, forget about tan H for the time being, right? This is OT element wise multiplication CT. Clear? So now the current hidden state will be updated. Now think what will happen at t plus 1. At t plus 1, again I will first initialize all the gates, right, which will be a function of the input at t plus 1, so xt plus 1, and the hidden state ht, right? And at time t plus 1 we will generate a cell content c tilde, right? And then the similar operations will basically be executed. Okay, now what is the guarantee that it will not have the vanishing gradient problem? What is the guarantee? Or can you intuitively state that the past information can be preserved for the longer time? If, let's say, if ft is 1, all the elements of ft are 1, all the elements of ft are 1, and all the elements of I are 0, then what will happen? So then then the cell state will get copied and copied, right? So ideally, if you do this, a token which is far from the current state, it will not be forgotten, right? But if you want to forget the cell state completely, then you fix f equals to 0 and I equals to 1. So these two gates will essentially control how much you want to forget, how much you want to retain, right? Now of course you have seen operations like tan h here, tan h here. These are all design decisions that they took. There are not proper justification behind taking this one, but these are all design decisions, right? And you have seen that this is passed through a sigmoid, right? The sigmoid will make sure that ft, it, and ot, they are just probabilities. Clear? Now can you see problems here? How many parameters are there? Now think of a vanilla RNN and an LSTM. LSTM is long short-term memory, right? How many parameters are there in vanilla RNN? How many parameters are there in LSTM? So in LSTM, you see, if you forget bias for the time being, right, you have 2 sets of parameters for every gate, right? And then also you have 2 sets of parameters for the cell content. There are so many parameters, and these are all matrices, remember this. Okay, so LSTM is generally useful when you have a lot of data to train, otherwise you'll overfit, right? If you have a lot of data to train, then only you can basically train all these parameters. So this is a diagram, pictorial diagram. You can I have already mentioned. So this is so each of these blocks indicates a particular timestamp, right? This is one block, this is another block, and so on and so forth. Okay, so remember, LSTM doesn't guarantee that it will remove vanishing gradient problem totally, right? But you can say that it will reduce the vanishing gradient problem compared to a vanilla RNN, right? In fact, there are other alternative ways of creating more direct and linear pass-through connections, right? We will discuss all these things later. Okay, so one way, so LSTM was one way. The other way to address vanishing gradient is what? Now remember, the vanishing gradient problem is not an unique problem for LSTM, right? Vanishing gradient problem is there in other models also. For example, if you think of a very deep feed-forward network, right? Very deep feed-forward network. If you are aware of transformer, for example, you know that transformer has multiple layers, right? 12 layers, right? 24 layers, 36 layers, and so on and so forth. So as we increase the number of layers, you see vanishing gradient problem, right? So as we increase the number of layers in simple CNN, simple RNN, simple feed-forward network, you see that the effect of the bottom layers to the loss, final loss, will be much lesser. So you see the bottom layers will not be updated at all. It will remain the same over the iterations, right? So another way to address this problem is something called a residual connection. This is also called skip connection. What is the residual connection? A residual connection says that, let's say you have a layer like this. Okay, a layer is nothing but a function, isn't it? It's a function, right? Let's say you this is your x, right? The input to that layer, and the layer output is f of x, right? And let's say you want to pass this f of x again to another layer, which is f dash x, right? And so on. So what you do in this residual connection, you essentially add the input to the output. So the input to the next layer will be fx plus x. Okay, again, when you generated f dash something, right, you feed this input here, right? You basically take a plus of this. Now what will happen is that due to so many complicated operations within each layer, right, the model will start forgetting the input itself, right? So every time you basically make it awake that please don't remember the input. You have an input and you should not forget that input, right? So you, at every step, you keep on adding this input again and again. We'll see this kind of skip connection in transformer when we discuss later. The other way to address this is let's say a dense connection, dense net, right? In dense net, what happens? Let's say you have RNN layers like this. Okay, so in a vanilla RNN, two consecutive layers are connected through one connection, right? In dense net, what you do, you connect all the layers to all its next layers, each of the layers to all its next layers. For example, this will, there's a connection from here to here, there's a connection from here to here, the connection from here to here, okay, from here to here, and so on and so forth. So every layer is connected to all the future layers. Not back connection, by the way, forward connection. Okay, so in that way you will always make sure that information will not be forgotten, because you have multiple connections. Of course, how to combine all these connections together would be a question, but there are ways, right? In fact, there are many other ways. There is another technique called highway connection, where you can use a gating mechanism. So highway connection is a mixture of a gating mechanism and dense net, right? So this is called highway net. In highway net, you use a gate to control. So you also have this dense connections and this gate. So gate will control how much you want to basically remember from the far away states, and how much you want to remember from the current state. Okay, the combination of this. Okay, then so LSTM was proposed long time back, by the way. long time back, and people did not use it because at that time, let's say early 2000, that time there was a scarcity of the amount of data, right? And then in 2014, so from 2008 2009, when people started curating data, huge amount of data, right? DenseNet, AlexNet, all these methods was proposed in 2011 2012. People got access to a huge amount of data sets. Then they thought that LSTM is okay, but let's look at other mechanisms. So in this paper in 2014, right, they proposed a mechanism called GRU, Gated Recurrent Unit. So in GRU, the idea is exactly the same as LSTM, right? The only difference is that here there is no explicit cell state, okay, and there are only two gates. One is called the update gate, which is responsible for controlling what parts of the hidden state are updated versus what to preserve. So there's only one state which is hidden state, right? You have to control. So this is what you have, right? So you want to control how much of the previous hidden state will be preserved and how much of the previous hidden state will be updated in the next hidden state. A reset gate controls what parts of the previous hidden states are used to compute the new content. Let's look at the equation. So similar to LSTM, here also I will basically initialize these two vectors, create these two vectors, gates, update gates and reset gate, and they are functions of the previous hidden state and the current input, same, right, with parameters, different parameters. Now this time here there is no cell content. Here there is something called hidden cell content that you want to insert into hidden state, right? Now this hidden state content H tilde, right, is essentially controlled by R. What is R? R is a reset gate, right? So R will decide how much of the previous hidden states will be used to generate the content, okay? And then so you generated the content which is H tilde, right, which is a function of the previous hidden state and the current input, right? And then this content will again be controlled by the update gate. So the update gate will decide. So there are two components now. One is the current hidden state, content that you generated, H tilde, and the previous hidden state, right? Then the update gate controls that how much of the current content will be moved to the current hidden state, and how much of the previous hidden state will be moved to the current hidden state, right? And you see they use a single gate, UT, right? So UT, and here UT and here 1 minus UT, right? So it basically balances. If UT is very high, then we'll give low weightage to the previous hidden state and more weightage to the current content. If UT is low, and then you basically do the opposite. Okay, so in this way we essentially control the entire thing. Now you see how many parameters are here. There are two parameter sets, two parameter matrices for U. There are two parameter matrices for R, and there are two parameter matrices for H tilde. Okay, so let's look at the comparison between LSTM and GRU. You can ask that which one is preferred, LSTM or GRU, right? In general, the practice, the suggestion is that you start with LSTM and then you move to GRU, right? If you have enough data. If you don't have enough data, you can use GRU, but this is the rule of thumb. You start with LSTM, you can switch it to GRU if you want something more efficient. But there is no clear evidence which one is better, LSTM or GRU. Sometimes LSTM performs better, sometimes GRU performs better. Okay, so this is about LSTM GRU. I already mentioned bidirectional RNN, right? In bidirectional RNN, you see this bidirectional arrow, right? So there is one forward RNN, right, which will generate hidden state at t. There is a backward RNN, right, which will generate a hidden state at t, and then the final hidden state at t is basically a concatenation of the backward RNN hidden state and forward RNN hidden state, right? And this kind of methods you use when you want to access to the entire sequence, right? Multi-layer RNN, you can also think of other variations where RNN layers are stacked one upon another, right? So this is one RNN, it can be bidirectional, unidirectional. This is another RNN, but look at here, what's the difference between bidirectional and multi-layer? In bidirectional, in bidirectional you have something like this. So this is a timestamp t, okay, where if this hidden state will be generated based on the current input xt and the previous hidden state ht plus 1, right, and xt. This hidden state will be generated based on xt and ht minus 1, right, and these two things will be combined. But in multi-layered RNN, you see here the input of every hidden state is not the actual input. What is the input? The input is the output of the previous hidden state, output of the hidden layer of the previous hidden state of the previous layer. See the difference between these two? Okay. LSTM has been very successful from 2013 to 2015, and then in 2017 transformer was proposed, and then people started using transformer. But again, the importance of LSTM kind of methods was realized recently. The state space model, Mamba kind of model, right? We will see that their RNN models will be used, right? RNN has its own beauty, right? But here also one problem still remains there. What's the problem? You cannot process the sequence in parallel. So you can't process the sequence in parallel, right? You have to wait till t minus 1 to basically process the hidden state at t, right? We'll see how we can address this. Okay, so this is all about LSTM GRU, right? In the next class, we will discuss sequence to sequence models and attention. Okay, thank you.